Oh, hello there. Welcome to today's lecture. So we have 8.3 we're going to start with, and then you will also watch 8.4 after this, I believe. So 8.3 is all about integer exponents. So just first an integer, sometimes we'll refer to it like we'll say in is inside of, that's what that kind of looks like, an E almost. And then this like weird double bar Z. That double bar Z is the set of all integers. What's an integer? Oh my God, what's a question mark? That's good. There we go. My question marks are twos with dots over them. It's just a whole number. And it can be negative, it can be 0, it can be positive. It's just not a decimal. 1, 2, 3, -1, not a million. Yeah, -1 million. But like 1/2, no, not an integer. So just a whole number. Alrighty. So when we talk about, oh, 1 second, forgot to pull something out. Oh, haha, I didn't. It's right in front of me. So when we're talking about exponents, this little n right here, this is what we would refer to as the exponent. And a right down here would be referred to as the base. And we would just say verbally a to the n, or you can even say a to the power. We also call exponents powers of n. And that exponent really just means a repetition of multiplication. So if I'm raising a to the n, what that means is a times a times a n times. Okay, so if I'm talking about 4 raised to the power 3, that means 4 times 4 times 4, right? And then that'll be what, 16 times 4, and then that'll be 64. Okay. This is kind of, these next two examples will really harp on the why parentheses are so important in mathematics, and also how to specify what the base is. So let's look at example 2 here. -2, the quantity -2 to the power 4. So in this case, my base is going to be -2. So this will be -2 times -2, oopsies, times -2, and so on, right? Which that'll just give me 4 times 4, which is 16. Okay. Well, down here on this third example, I have -2 to the power 4. So what's my base here? My base is actually just 2. So this would be like a -1 times 2 to the 4th. That's another way of thinking about it. So that'll be like negative, because the negative sign we can always just think as like a hidden -1. So it'd be like -1 times 2 times 2 times 2 times 2, which will actually give us -16. So the difference in the bases is really important because you can see how different these answers are. And you're like, well, because one's positive 16, one's -16. Yeah, but if I'm like calculating something and I forget that negative, especially if you're putting in your calculator will know the difference between these two and spit out a wrong number. Okay. So just be careful with your base, so that parentheses always makes it clear what our base is. Okay. So those were all cases where our power was a positive number, 3, 4. Remember, we're all only doing whole numbers right now, so they're all integers. And we talked about if the base is positive and negative, and if how to specify that negativity in the base, right? So what if our exponent is negative? So in this definition, we see that if a is not equal to 0, because we'll explain why a can't be 0 in a second. Then I can say a to the negative n is going to be equal to 1 divided by a to the n. So we can also see that this says negative exponents correlate to the reciprocal. So the reciprocal, remember, I might have said it before, you just flip it. I learned in algebra that if you think about it, is your fraction as like a house. So the denominator is downstairs, your numerator is upstairs. Everything, if it's not like a fraction, it's just, you can think of it as over 1. So a to the negative n, the exponent is negative. It's not a happy exponent. So the way that we can make it a happy exponent is by moving it downstairs. So if nothing's there anymore, it's not going to be 0. It's going to be a 1. If it was 0, the whole thing would be 0. And I'm going to put a to the n. And now the exponent is positive because it's happy there, because it wasn't happy in the first place. So you just move where it is in the house and its attitude changes. And vice versa. If I have something like this, I can go this way as well with the same idea. You're like, Minzy, why are you telling me about this house? It seems like so easy. When we bring in more exponent rules, I often see people try to make the exponent into a fraction. They'll see a negative and be like, I know there's a fraction somewhere, or make something into a fraction. And then they make a to like the 1 over n, which we'll talk about that. And I think A4. So if the exponent is negative, move it to the other side of the fraction. And same goes if it's in the denominator. If it's negative, it'll be positive when we move up to the numerator. Okay. Anything else I wanted to say on that? The reason that a cannot equal 0 is 0 raised to any power is 0. And I cannot ever have 0 in the denominator because I can't divide by 0. If you have an iPhone, ask Siri what 0 divided by 0 is, and she'll give you a funny answer. Okay, so let's go into properties of exponents. So we just saw that -1. That was pretty cool. But let's see how exponents work with multiplication and division. Okay, so if I have two things with the bases are the same, but my exponents are different, they can also be the same. And they're multiplying them, so bases are the same and they're multiplied. So the base is still going to be the same. That's not changing. But now my exponent, I'm going to add them. And this kind of makes sense. I'm doing a times a times a times a m times, and then I'm going to do a times a times a times n times. So how many times? M times, and then I'm multiplying another n times. So I'm going to add them together, m plus n. Okay. Property number 2 is division. So a to the m divided by a to the n. Again, same basis, but now I'm doing division. So if I multiply and they add together, the dividing, I should subtract them. Good job. I hope you said subtraction. All right. And this comes from different things. Remember how I talked about if I have something in the denominator, I can move it to the numerator or just flip the sign of the exponent. So I can write this as a to the m, oopsies, times a to the negative n. Those things are the same. And then m, I can use property 1, a to the m plus negative n, which will get me to the same place again. So So that's like a small proof to how that works. Okay, so now what if two things are in the base? So now I have two different bases. So I have a times b raised to the m. We can also just say ab. When letters are next to each other, we assume that there's two different variables. And so if I have two numbers multiplied to each other raised to the m, I can distribute that exponent. I'm only distributing that exponent over multiplication, okay? So this m goes to both things. A to the m times b to the m. This does not work with subtraction and addition. Okay, and we'll talk about that in a little bit. So I can distribute exponents over multiplication. Great, that's really handy. Remember, things usually work out with multiplication. Now I have one base and I have two different exponents. I'm first going to raise a to the m, and then I'm going to take that quantity and raise it to the n. So if we think about the definition of what the exponent is, that would be like a to the m times a to the m times da da da, however big n is, n times. But each a to the m is a times a times a, m times. So I have a times itself, m times, again and again, all the way to n times. So I already saw where a to the n plus n, n minus n. So what do we think the exponents are going to do here? We've already seen addition and subtraction. They're going to multiply together. Oopsies. So I would just multiply those two exponents together. Okay. And then property 5 should have been a little closer to property 3. But because they're similar, right? This is just the division version of 3. So if I have a divided by b, two numbers, a fraction, raised to the n power, I can put that power or exponent on the numerator and denominator with no problem. So this would be a to the m divided by b to the m. All right, cool. Now, remember, a, b, and m and n are all real numbers. Specifically, m and n are integers because we're only talking about integer exponents. So property 6, I have a raised to the 0 power. So any number raised to the 0 power is always going to be the same number, which is pretty cool. And that number is 1. And we'll go over that proof in just a second. So all of these are actually derived from the definition of exponents, which we've kind of talked about. But how do we get a to the 0 to be 1? Well, if we think about, let's talk about 2. So 2 cubed is 8. Well, if I wanted to find out what 2 squared was, one exponent lower, I would divide 8 divided by 2. I would take one exponent, I would take 1 2 away, right? Oh, that would give me 4. And then, right, because each time I'm multiplying by n times, so if I want to go down, I should, opposite of multiplication is division. Well, then if I wanted to find 2 to the first, I would take 4 and divide by 2. That's just 2. And that makes sense. And then if I wanted to find 2 to the 0, I would take 2 and divide it by 2. Well, that's just 1. And that works for any number. And you can think about it in general as well. A to the 0, we can say that's a to the, anything minus itself is also 0. So n minus n, sometimes I'll also refer to that as a fancy 0. It's kind of like our fancy 1 is any number divided by itself. A fancy 0 is any number minus itself. So, well, I know that that's going to be using this number 2 up here. Well, that's just going to be a to the n divided by a to the n. Well, anything divided by itself is just 1. So that's another way to think about it. I like this first one a little bit more because you actually get like real numbers to think about. All right, so try that on another number and it'll work for any number. It's pretty cool. All right, so now let's put these properties in to work. All right. This one we've kind of already done. We would say, oh, this is a to the n minus. So use exponent properties to simplify each expression. Just to clarify, an expression is just like like this. There's no equal to sign. That's an equation. So it's an expression. It's kind of like the middle of a sentence. 1 second. I left my freezer door open. How do I pause recording? Okay. Sorry. I grabbed some cookie dough out of the freezer and then I forgot to close it all the way. So we're simplifying these expressions. Yeah. So we can kind of rewrite the proof that we just wrote, right? If I have a to the n minus n, that'll be a to the n divided by a to the n, which is, you can also think about it, oh, each of these have their own exponent. So I can pull it out, a over a is n. This is another way of thinking about it. Okay, well, a over a, that's just 1. And n raised to any power is also 1. 1 times 1 times 1 times 1, except if n is infinity. I wrote that in my college essay. I didn't get accepted into that college. And that's so another way that we can think about a to the 0. I just kind of added the extra step from here to here out of these middle 2 steps. Okay. So now let's do number 3. So I like to work in the beginning step by step. So like I don't want to do 2 steps at once because sometimes it's confusing me, like, oh wait, how do I get that? Da da da, if I do like multiple steps. So I like to first work on the numerator and then the denominator. So if we focus on the numerator, I have 3 to the 6th times 3 to the negative 2, and everything is divided by 3. So if I'm looking at the numerator, these 2 bases are the same. So my exponents are going to add. So I have 3 to the 6 plus negative 2 divided by 3. And we can say used property 1. You don't have to write that next to it, but if that helps you, by all means. All right, and then I'm going to simplify that exponent. So 6 minus 2 is 4 divided by 3. All right, and then go over here. Now, this 3 is kind of has like a to the 1, kind of hidden it. So now what property should I use? What property should we use? I have divided sign, and can I use this one? No, my bases are the same. That's not useful. I'm going to use property 2, where I have the same bases, but they have different exponents. So this is going to be 3 to the 4th, 3 to the 1. So that's going to be 3 to the 4 minus 1. So used 42. And that's going to simplify to the 3 to the 3rd. And then that's something easy that I can calculate. I think it's 27. And we're good to go. So how will we know that I've simplified an expression down to as much as I can get it? Well, if I have only numbers involved, I want just a number back out. I don't want 3 cubed. That number to me seems pretty easy. If it's like 5 to the 100, I don't know. That one seems pretty, if I can put it into a calculator and figure it out, I think you guys can write it out all the way. So I would prefer 27 rather than 3 to the cubed. or 3 to the third. All right. But as we see in number 3, I don't have numbers. Now I have variables involved. That's what we call those letters. Okay. So moving on to example 3, it's simplified when there's only one of each variable and only one number. And I'll catch back up to that when we finish this one. Okay. So, excuse me, these multiplication things are just kind of separating these, what we would call, not terms, factors. They're multiplied together. All right. So I'm not going to distribute to each one. Then I'd be doing 3 times 3 times 3, and that's different things. So I can think about this as saying 3 times x squared times y cubed times -4 times x to the -2 times y to the -5. So that's all it's saying. I don't need to distribute here at all. All right. So I like to love organization. I'm going to get my numbers together and then usually my variables in alphabetic order, but it doesn't really matter. So I'll do like 3 times -4 times x squared times x to the -2 times y cubed times y to the -5. And that just makes our work a little easier. So 3 times -4, that's going to give us -12. And then I'm going to use property A again, sorry, 1. But I'm kind of doing the reverse. Actually, no, I'm not. I have the same base. They're both x. So I'll have x, and then it'll be 2 minus 2, and then y cubed times y to the -5. That'll be 3 minus 5. And then -12, there's nothing special about that. X to the 2 minus 2, that's x to the 0, y, 3 minus 5, that's going to be -2. All right, so now I'm not done simplifying, right? I told you we need a number and then one of each of our variables, but there's more that we can do. I know there's more properties that I can apply. Well, I know that x to the 0, that's going to equal 1. So it's going to be -12 times 1. And then it should specify, and I always specify on my exams, negative exponents. Write your answer only in positive exponents. So let's say want only positive exponents. Okay, so if y has a negative exponent, it's technically in the numerator right now, it's hidden, then I need to bring it to the denominator. And that'll give me my positive exponent. And then I can just write it a little nicer because times 1 is kind of redundant. And that's how we can get to -12 over y squared. Okay, it's fine that we don't have an x involved because I know just x to the 0 is just 1, excuse me. Okay, so when we talk about simplifying, I only want positive exponents. Okay. All right, so we did one with multiplication, so now let's do one with division. So my variables here are a and b. So I have -6 times a to the 5, b to the -1, divided by 2, a to the 7th, b to the -3. Again, there's lots of different ways to do this. My suggestion is to handle the constants, so just the numbers on their own. Excuse me. And then bring all the variables to the numerator. So what that's going to look like, it's going to be negative 6 divided by 2, a to the 5, b to the negative 1, a to the negative 7, and b to the negative 3, right? So then I can go ahead and kind of do what I did in the second step up here. I'm going to simplify negative 6 divided by 2, and that's going to give me negative 3 times a to the 5th, a to the negative 7, kind of grouping things up by their bases. Right? Did I write that right? Okay, cool. All right, and then using property 1 again, negative 3 isn't really, there's nothing else, it's not special. So a to the 5 times a to the negative 7. So this is going to be a to the 5 minus 7 times b to the negative 1 plus negative 3. Something like that. Or you can just say minus 3. Boop, boop. Okay. Oh, what did I mess up? That negative 3 came from the denominator, so it actually needs to be a positive 3. There we go. Because it wasn't happy down in the denominator, and I brought it up where it was happy in the numerator, and I forgot to make it happy. Positive exponent. And you're like, Mackenzie, that kind of like seems like a really immature thing. I swear, it really helps you remember. And if it's silly, but it helps you remember it, who cares? All right, so negative 3, it's still chilling, not doing anything. A to the 5 minus 7 is going to be a squared. And this is basically 3 minus 1. And that's going to be b squared. I know. A to the minus 2, there we go. And then again, we don't want negative exponents, so I can get rid of that by banishing a down to the denominator. He's not really banished, he's very happy there. He's having a great time. Okay? So if you're still a little confused on these, we have one more to do. And then your homework will be a lot of practicing on this. All right. So last one. So we talked about multiplication, division, and now I have this basically just to the 4, right? So I have negative 3x to the a minus 5 and y to the negative 3. So remember, exponents distribute over multiplication. So everybody's going to get a 4. So this is going to be negative 3. So negative 3 is my base here to the 4 times x to the a minus 5 to the 4 and y minus 3 to the 4. So now I think this is going to be property 4. Yes. Where it says that when I have something like this, I can just multiply those exponents. So negative 3 to the 4, that's the same as 9 squared, which is 81. And then this is going to be x to the 4 times a minus 5 and y to the 4 times negative 3. And then we can go on and simplify. You can distribute that 4 to the a minus 5 if you want to. So you'll get like 4a minus 4 times 5 is 20. And then y to the negative 12. So then we don't really like negative exponents too much. So we'll do x to the 4a minus 20 divided by y to the 12th. Well, what about that minus 20? Is that fine in the denominator? Yeah, absolutely. We don't really want like a negative integer, really. But it's fine that there's like a subtraction in this expression right here. But if the whole thing was like negative, like negative 8/4 minus 20, then I'd probably be like, you can also move it downstairs. I'm more harping on that is in the denominator. That's my main concern. Alrighty. So that actually finishes up 8.3. So I will see you in the next lecture.